Yeah, welcome back to next session, students. Here we are going to see filtering, amplification, and linearization. These are the three important signal conditioning processes that we are going to see in this session. We have seen the basics in earlier session. Now we'll start the filtering, amplification, and linearization. Amplification. An amplifier can be considered to be the essentially a system which has an input and an output. The voltage gain of the amplifier being the ratio of the output and input voltages when each is measured the relative to the earth. So here this is a simple amplifier, and it consists of an input and an output, and also it has voltage gain. So that is the input to output ratio. So output and input ratios, and with that gain, how much we are going to amplify. So this is the factor, right? This is the major factor with which we are going to amplify the signal. The input impedance of an amplifier is defined as the input voltage divided by the input current. So that is input impedance. The in output impedance being the output voltage divided by the output current. So voltage by current is normally impedance, and the basis of many signal conditioning modules is the operational amplifier. So this is the main unit, and without this there is no signal conditioning itself. So the main unit in any signal conditioning unit is op-amp, operational amplifier. The op-amp is a high gain DC amplifier. It is a DC device, and gain typically being of the order of 1 lakh or more. So it comes as an integrated circuit on a silicon chip. So it is a silicon chip only. I will show you its configuration. It has two inputs known as the inverting input and the non-inverting input. So non-inverting input is plus terminal, and inverting input is minus terminal. The output depends on the connections made to these inputs. There are other inputs in the operational amplifier, namely as negative voltage supply, a positive voltage supply, and two inputs termed offset null, and these being to enable corrections to be made on the non-ideal behavior of the amplifier. If it is exhibiting any non-ideal behavior, then we have to make corrections through these additional inputs, additional terminals. So the first is amplifier. The pin connections for a 741 type operational amplifier is I will show you in the next diagram. An ideal model for an operational amplifier is an amplifier with an infinite gain, infinite input impedance, and zero output impedance, i.e., so that is these are the ideal characteristics of any operational amplifier. The output voltage is independent of the load. So here this is input current, output current. We have output voltage, input voltage. So this is the amplifier. A simplified diagram. This is the simplified diagram. In next slide, I am going to show you the complete terminals of the amplifier. So this is the 741 operation amplifier. So this is a type, and these are the this is the symbol for operation amplifier. It has two terminals in non-inverting and inverting, and these are the other terminals like positive voltage. This is output, and we have offset null, and we have negative voltage and offset null. So this is the notch. From here we have to count the pins from left hand side in counterclockwise direction. 1 2 3 4 5 6 7 8. So it is having 8 pins. So this is 3 pin is non-inverting input, second pin is inverting input. So this is a simple diagram of operation amplifier. this is the example I have taken here, 741 operational amplifier. So here, ideal op-amp characteristics, as I said in earlier slide, ideally op-amps have characteristics used in circuit analysis: infinite voltage gain, infinite input impedance, does not load the driving sources, and zero output impedance, drive any load, infinite bandwidth, flat magnitude response, zero phase shift, zero input offset voltage. The ideal op-amp has characteristics that simplify analysis of op-amp circuits. The concept of infinite input impedance is particularly a valuable analysis tool for several op-amp configurations. So here, infinite input impedance is an important characteristic with which we can study many op-amp characteristics, many op-amp configurations. So here, these are the few terms that we should know in op-amps. The first one, operational amplifier, a type of amplifier that has very high input gain, very high input impedance, very low output impedance. This is very important, low output impedance, but high input impedance, and good rejection of common mode signals. So the CMRR should be good. And differential mode, a mode of op-amp operation in which two opposite polarity signals voltages are applied to the input, to the two inputs, so double-ended, or in which a signal is applied to one input and ground to the other input, so it is single-ended. So double-ended and single-ended, there are two modes. So these two are differential mode. Common mode, a condition characterized by the presence of same signal on both inputs. So that becomes a common mode. Slew rate, it is a very important 2 mark question as well. The slew rate is the maximum rate of change of the output voltage in response to a step input voltage. So this is a slew rate. This is again important 2 mark question. So these are all the 2 mark questions also. So here, open loop voltage gain, the voltage gain of an op-amp without external feedback. So that is open loop voltage gain. Negative feedback, the process of returning a portion of the output signal to the input. So that is feedback of an amplifier such that it is out of phase with the input. So that is negative feedback. And closed loop voltage gain, the voltage gain of an op-amp with external feedback. So gain bandwidth product, a constant parameter which is always equal to the frequency at which the op-amp's open loop gain is unity. So that is gain bandwidth product. So these are the important key terms. Any one can be your 2 mark question, and I should prepare all. So next is filtering. The term filtering is used to describe the process of removing a certain band of frequencies from a signal and permitting others to be transmitted. So, a certain band is removed, and the other from signal, and permitting others to be transmitted. The range of frequencies passed by filter is known as pass band. So which are allowed are known as pass band. The range not passed as the stop band, and the boundary between stopping and passing as the cutoff frequency. Filters are classified according to the frequency ranges they transmit or reject. A low pass filter, I will show you in next slide, has a pass band which allows all frequencies from 0 up to some frequency to be transmitted. So that is a low pass filter. High pass filter, has a pass band which allows all frequencies from some value up to infinite to be transmitted. So a band pass filter allows all the frequencies within a specified band to be transmitted. A band stop filter, so a certain band is stopped, stops all frequencies with a particular band from being transmitted. In all cases, cutoff frequency is defined as being that which the input voltage is 70.7% of the of that in passband. So these are the five types of filters. So next, the attenuation is a very important term in this operation amplifiers. The term attenuation is used for the ratio of the input and output powers. This being written as the ratio of the logarithm of the ratios, so gives the attenuation in units of bells. So attenuation is the actually the ratio of input and output powers, and it is represented in terms of logarithm of the ratio, and it is represented in bells. And since this is a rather large unit, decibels dB are used, and then attenuation in dB, input power to output power. Since the power through an impedance is proportional to the square of the voltage, the attenuation in decibels, input voltage to output voltage. The output voltage of 70.7 percentage of that is passband is thus an attenuation of 3 decibels. So it is a small calculation here, 70.7 percentage. So this is attenuation. Attenuation is also an important 2 mark question. So characteristics of ideal filters. First one is low pass filter. So it allows the low frequency band, pass band, and from certain band, it is the next one is high pass. So high frequency signals are becoming the pass band here, and band pass certain frequencies are becoming pass band here, and band stop certain frequencies are stopped. So certain frequencies are stopped. Pass bands are except certain frequencies are stopped. So here you will have more number of pass bands on either side of the stop band. So these are the four types. So the term passive is used to describe a filter made up using only resistors, capacitors, and inductors. So passive circuit is consists of all these three elements: resistors, capacitors, and inductors. The term active being used in the filter also involves an operational amplifier. So here the active will have the filter and also having an operational amplifier. Passive filters have the disadvantage that the current that is drawn by the item that follows can change the frequency characteristic of the filter. This problem does not occur with an AC active filter. Low pass filters are very commonly used as part of signal conditioning. This is because most of the useful information being transmitted is low frequency. Since noise tends to occur at high frequencies, a low pass filter can be used to block it off. Thus, a low pass filter might be selected with a cutoff frequency of 40 Hz, thus blocking off any interference signals from the AC main supply and the noise is in general. So next I will show you the diagram. So here the low pass filter, passive, active. So this is passive, only it consists of R and C, whereas active it consists of operational amplifier also. So that is the active using operational amplifier. So here you have resistor or the resistor here, capacitor is connected across this amplifier, and this is inverting terminal and this is non-inverting terminal of operational amplifier. This is the active circuit. Next is linearization. The intrinsic nonlinear response of some sensors is one of the complex problems in the field of signal processing and sensor interface. The remedial procedure known as linearization, this converts nonlinear output into a linear one, making it easier to process and comprehend data in the future. So the linearization is such an important process. Why some sensor outputs need linearization? So the output of many sensors is not linear over their whole measurement range. A nonlinear relationship between magnetic field strength and output voltage may be seen in some magnetic field sensors as well as in the thermistors, where resistance changes non-linearly with temperature. Direct readings might be defective or difficult to understand when a sensor produces nonlinear output. Hence, linearizing the output of the sensor becomes essential for precise measurement of utilizing its full potential. So that is the linearization uses, and there are some techniques to achieve this linearization. Techniques for linearization using electronic circuits. To linearize sensor outputs, hardware solutions frequently use different circuit architectures. Op-amps are also used for linearization. The output can be efficiently linearized by configuring op-amp configurations to offer the inverse of the non-linearity of the sensor. Sensors like as thermistors are frequently used with this technique. Compensating networks, these circuits, which are frequently composed of capacitors, resistors, and occasionally inductors, are intended to respond in a way that offsets the nonlinear behavior of the sensor, that actually suppresses the nonlinear behavior. So there are software methods also. Software based linearization has grown in popularity as microcontrollers and digital systems are integrated into sensor interfaces more and more frequently. So there are lookup tables also. The nonlinear sensor output and a linearized value are correlated using a predetermined table. This system looks for the matching linear values of this table when the sensor gives a reading. So these are the few techniques, and also polynomial correction. The nonlinear behavior of the sensor is represented by mathematical models which are frequently in the form of polynomial equations. Subsequently, the output of the sensor is linearized and corrected in real time using this model. So curve fitting algorithms, the best fit curve for the sensor's output can be found using sophisticated algorithms. After it is established, further readings can be linearized using this curve. So, in contrast, to summarize this, the process of linearization is essential for guaranteeing consistent, dependable, and easy interpreted sensor outputs. It is a crucial component of contemporary sensor interface, providing the groundwork for precise data collection and analysis, regardless of how it is accomplished through electronic circuits or software algorithms. So these are the linearization techniques. Both way there are different methods, including software or manipulating the hardware. There are different methods available. So here even these topics are very clearly given in Rai Chaudhary book, Linear Integrated Circuits. So there ends this topic. In next session we will meet again. Thank you, students.